Hello everyone, my name is Yuanyi. I was a PhD student at Penn State University. Today, I would like to share our work, ZoomP3, Privacy Preserving Publication of Online Video Conference Recordings. This is a joint work with Professor Sencun and Professor Chen. Recently, due to the impact of epidemic, video conference applications have become increasingly popular, such as Zoom, Google Meet, and Microsoft Teams. Video conference applications are suitable for different scenarios, such as entertainment video conference. In this example video, the participants in the meeting express their feelings. Let's take a quick look of this video.
Just reset the camera.
Okay, like this. Did I activate Zoom?
Nope, you turned it off.
The following demo is more formal for business video conference, where participants speak one by one. Let's take a quick look of this short video.
Started and hopefully over the next few years get them coming back and work on that showcase.
So what's the actual funding?
There is a lot of personally identifiable information that is exposed in the meeting, including face, name tags, and voice. There will be significant privacy concern once the video contains this PII are released to the public website like of YouTube. The previous user study has shown that video conference recordings are ideal for an attacker to collect the user data. An attacker can crawl a large number of VCRs to extract their facial information and corresponding participants' name, determine the participants' age and gender. If such a database is sold by the attacker, the purchaser may either target the victim with the advertisement or make use of information to impersonate the victim. In this research, we aim to address the above privacy risk by proposing an automated and efficient video privacy preserving system for protecting VCRs. Here are some preliminary to know. All videos are made up of a number of continuous images. Each of the images is called a frame. There are several different modes in the video conference, including speaker view, grid view, and the share screen mode. They have a different window layout. In our system, we have two types of users. One is called public users, which refer to those who allowed their PII to be disclosed with the video. And the other one is called privacy-sensitive user, which refer to those who do not allow their PII to be disclosed with the video. In our system, there are two protection modes, whitelist and blacklist. In a whitelist mode, for example, if a professor teaches a 15-minute class, then the professor is a public user. All students participant in class are privacy-sensitive users, and we expect all students' PII to be protected. Blacklist mode, for example, for a conference video, the user Alice explicitly requires the conference host to remove her PII from the video. Here is our system workflow. For example, if there is an original video that needs privacy protection, then the first step is to select the target user's face regions and voice interval. Then execute the privacy protection model and finally run the video patching system to fix any possible protection leakage and finally get the final video. In our system, the privacy protection model is the key model. As shown in the figure on the right, it will separate the video into video and audio respectively for privacy protection and reassemble the video and audio into the final video. As mentioned before, face area is a part of PII. We need to locate the face area that is face detection. Here, we introduce some face detection algorithm with their advantage and disadvantage. For example, theta face, which is lightweight and fast, but has the disadvantage of not being able to detect small face. DB face is good at detecting small face, but has a lower performance. Face recognition or face identification is to answer the question of who is the face. Since we are mainly targeting conference video and the vast majority users are close enough to the camera, we use theta face for both the face detection and face recognition by default to improve the performance. The figure on the right is the result of face protection. You can see that all faces are protected. How to make the whole process privacy protection scalable? The simplest way is frame by frame protection. Face detection is applied to each frame of the video, followed by the face identification. If a sensitive face identified in a frame, it will be blurred. Then comes with our proposed graded backward processing. Because a large number of the frames are extremely similar, we divide the video into groups and select one keyframe to represent the group. Face detection and face identification are only conducted on the keyframe in each group. For each non-keyframe, it will be precise according to the face detection and face recognition result of the two keyframes before and after it. Here is an example. This video has a totally 6 frames, alternating between Bob and Alice. Bob is a public user and Alice is privacy sensitive users. The group size is 3, so the third and the 6th frames are keyframes. And the first frame is also listed as the keyframe because it is the beginning of the video. The first frame came in, the first frame is a keyframe, so performs the face detection and face recognition and puts the result into the cache. The second frame is not keyframe and directly put it into the cache. The third frame is a keyframe and processed as the first frame. And at this point, the cache has reached 3 frames, and the third frame is inferred according to the keyframe before and after it. Since Alice appears in the third frame, it is possible that Alice also appears in the second frame, so the area corresponding to the second frame is protected. The fourth frame is not keyframe and processed as the second frame. The fifth frame is same. The sixth frame is keyframe and processed according to the third frame. Here is our final result. The final video below shows that although there is a overprotection in the second and the fifth frames, it ensures that the frames associated with Alice are protected. Obviously, if the group size is increased, the performance can be improved significantly. If there is no speaker change in your group, we can increase the size of the group to reduce the computation. How to detect speaker change? We use the perceptual hash to detect the speaker change. In the speaker wheel mode, only when the speaker is changed, there will be a dramatic change in 2 adjacent frames. We use this approach to increase the group size and make the system more efficient. In this presentation, we have only covered the face privacy protection. The audio protection is based on the speaker diarization, then protect the voice to ensure that the voice cannot identified. Speaker diarization is precise to partition an audio stream with multiple people into homogeneous segments based on the speaker identity. For example, in the figure below, we can output the similarity value of each speaker at the moment. Using the speaker's information, we protect the voice and add randomness to a certain speaker's interval so that the attacker will not be able to restore the original voice. The name tag protection is based on the OCR to protect the sensitive text information. As shown in the figure below, given an image, output are the all embedded text as well as the coordinates of the bounding box of each character. During the whitelist and blacklist modes, based on some information such as location and size, we can find out all the text areas that need to be protected. Then we can protect all the tags need to be protected. Due to the time constraints, please see the paper for detail on the privacy protection of audio and name tags. The processing time varies along with the length of video. The number of people in the video and the frequency since switching differ among the videos. We use the SNL videos as an example to test. Here is the result. Let's take a quick look.
Just reset the camera.
Okay, like this.
In this demo, the mine is public users, others are privacy sensitive users. From the demo, you can see that all privacy sensitive users' face, name tag, and voice are protected. Evaluation. We choose a group size of 5 and 4 parallel computations. We can reduce a video processing time from the 800 seconds to 62 seconds. Conclusion. We introduced ZoomP3, a practical privacy preserving published system for protecting both the video and audio of privacy sensitive participants in online meeting. We will investigate how to segment the Zoom windows more precisely, and we will investigate how to make the diarization more accurate. Thank you.